Welcome to this explainer. Today, we're going to uncover the invisible, microscopic mechanics that literally dictate our physical reality. We are looking at the hidden forces of chemistry that awaken the very second you mix two different things together. So let me ask you this. Why do we salt icy roads in winter? I mean, you've probably seen the trucks dumping it, or maybe you've even scattered it on your own driveway. Now, the standard everyday answer is just, well, it melts the ice. But that's really only half the story. The true answer is actually this fascinating microscopic dance of particles. And by the time we wrap up here, you're going to understand exactly how this works on a molecular level. Okay, let's dive into this with Section 1, the anatomy of a solution. At its core, a solution is just a homogeneous mixture. It's simply a solute, like sugar, dissolved evenly into a solvent, like water. But the absolutely crucial insight here is that the exact moment dissolution happens, the fundamental physical rules of that liquid are completely rewritten. It is no longer just your baseline solvent. Those molecules are now bound by entirely new interactions. Now, to really understand these new interactions, we have to measure concentration. But chemists face a very practical, real-world dilemma here. You see, molarity measures moles per liter, but volume actually expands and contracts with temperature. So a solution mixed in a freezing cold garage technically has a different molarity than one sitting in a boiling hot lab. And that's exactly why real-world science often relies on molality instead. By measuring based on the mass of the solvent, specifically 1 kilogram, those temperature fluctuations become totally irrelevant. Because mass never changes, the math becomes basically bulletproof. Moving right along to Section 2, Raoult's Law and Vapor. In an ideal world, which is governed by Raoult's law, molecules mix without any drama. Vapor pressure is basically just the gas trying to escape the surface of the liquid. But if you drop in a non-volatile solute, like salt, for example, those new molecules start crowding the surface. They don't evaporate, but they physically take up space. They act like these microscopic blockades. And with fewer solvent molecules exposed to the open air, the overall vapor pressure naturally has to drop. But what happens when things aren't so ideal? That brings us to Section 3, when solutions break rules. You know, what actually happens when chemical roommates are completely dysfunctional? Let's look at positive deviation. Mix ethanol and acetone, and their intermolecular interactions are actually weaker together than they were apart. They basically want to avoid each other, so they eagerly escape into the air, and that causes a massive spike in vapor pressure, way beyond what Raoults would predict. On the flip side, we have negative deviation. This happens when molecules cling tightly to one another. Acetone and chloroform bond so strongly that very few escape as vapor, and the pressure unexpectedly plummets. And this brilliantly illustrates our next topic, Section 4, the colligative property magic. This brings us to a massive leap in chemical logic called colligative properties. We're talking about the relative lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, and osmotic pressure. Do you want to know the magical secret that unites all four of these? They depend entirely on the sheer quantity of particles added, not their identity. Sugar, urea, salt, it honestly doesn't matter. 10,000 particles of one act exactly like 10,000 particles of another. It is purely 100% a numbers game. Which brings us directly back to our hook from the beginning, those icy winter roads. Adding any solute causes structural interference. It physically prevents the solvent molecules from easily locking together into a solid ice crystal. So to force them to freeze, you have to drop the temperature significantly lower. By covering an asphalt road in a massive number of salt particles, we are artificially depressing the freezing point of water. Sometimes we push it down to minus 18 degrees Celsius. The ice is literally forced to melt into a puddle simply because those extra particles are crashing the freezing process. Now, another incredibly vital colligative property is osmotic pressure. Osmosis is just the natural flow of a solvent through a semi-permeable membrane. It moves from a dilute side over to a concentrated side, just trying to find balance. Osmotic pressure is simply the exact mechanical force required to stop that flow from happening. And this is a total game changer for biologists. Because this pressure can be calculated at comfortable room temperatures, it is by far the most accurate way to measure the mass of really fragile micromolecules, things like human biological proteins. If you tried to use boiling or freezing to measure them, you'd completely destroy them. Just when you think the math is perfectly settled, we hit Section 5, the Van 't Hoff twist. Okay, so we just established that colligative properties only care about the total number of particles. But what if the particles lie?
In a process called association, particles in substances like acetic acid actually clump together when they're in solution. Two particles act like one, which artificially decreases the total count. But conversely, with dissociation, compounds like our trusty road salt, sodium chloride, actually split apart. They break into distinct positive and negative ions the very second they hit the water, instantly multiplying the particle count. This unexpected clumping or splitting throws all our standard calculations totally out of whack. So the crucial point is how we fix this. Chemists use something called the Van Hoff factor, represented by the letter I. It represents the ratio of the actual particles in the liquid compared to what we initially expected there to be. For our road salt, I is greater than 1. Because a single molecule of sodium chloride breaks into two ions, its impact on the ice is effectively multiplied. It is doing double the work. The invisible math perfectly dictates the physical reality you see out on the road.
We've seen how manipulating particle counts can melt treacherous ice on winter roads, and how osmotic pressure lets us safely measure the vital proteins inside our own bodies. We even use reversed osmotic pressure on a massive industrial scale, literally pushing fresh water out of salty seawater to provide drinking water for millions of people. So consider this. If manipulating microscopic particle counts can purify the oceans, what other massive macroscopic challenges in our world can chemistry solve? Keep questioning the invisible forces around you, and thanks so much for joining me on this explainer.